So today we're going to start talking about what's called conditional probability. And the conditional part means if one thing happens, how does that affect the next event? So, for instance, here, okay, you'll see the word given a lot. Given that event A has already occurred, find the probability that event B occurs after this. So, for instance, if we want to do a little bit simpler of a one, over here we've got this spinner. Naomi's playing this game with the spinner shown. What's the probability that the spinner lands on 7 given that Naomi has spun a number greater than 5? So here's how we kind of put this together. We look and we say, okay, now here's our fancy business. We always get the fancy mathematical lingo here first and then simplify it. So I look and I go, okay, so there's 8 possible results, 8 possible numbers. All right. So A is the event that she spun a number greater than 5, okay, because that's what we assume happened first. Well, there would be 3 outcomes that are greater than 5, 6, 7, and 8. So that's where this probability A is coming from. The probability of both things occurring, that she spun a number greater than 5 and that the event is a 7, okay, would be just this, that she spun a 7, would be just this single one. So here's how this works in English. I like calling this the end result over the given. Whenever you find these words and you see the word given in the middle, you take whatever is after that, that's going to be your denominator. What you're attempting to find, what's the probability that the spinner lands on 7, is what would go up here. So what I'm basically doing here is I'm taking, okay, what's the chances the spinner lands on 7? 1 out of 8. Divided by the given that the number was greater than 5. 1, 2, 3 out of 8. And then I just divide them. Well, if you divide with a fraction, we know you multiply by its reciprocal. And what will happen with these more often than not is that you'll get 2 values that cancel, and we'd find out the probability of spinning a 7 if the number is greater than 5 is 1 in 3. Now, pretty quickly, some of you are going to find there's going to be a shortcut to this. When one of you sees it, we'll stop and we'll discuss it, because there is a little bit faster of a way. But again, we like letting you see mathematically where it comes from. Some of the things here are going to talk about cards. Now, I have learned from past years that not everybody is an aficionado with how cards work. So let's get a little bit of information for you here. When you're dealing with cards, there are 4 suits that each have 13 cards. Okay, so you have hearts, diamonds, spades, and clubs. Another thing that comes up, people are like, what? It's what's called a face card. Face cards are the jack, queen, and king. Okay, so there are 12 total, and there's 3 of each suit. Okay. Those are the things that tend to get people the most. The one other thing I'll mention, in the 4 suits, 2 of them are black and 2 of them are red, which of course means half the cards are red and half the cards are black. And again, if you haven't done a lot of things with cards, that may be something you don't know right away. So it's something I like to get out there to be able to help out with. So we're going to have these cards, and they're going to get drawn from a standard deck of 52 cards. Find the probability. Now again, this is me. If I see the word given in any of these, what's after that is going to be my denominator of my fraction that I make. Whatever I have at the beginning is my end result, what I'm trying to actually get my probability for. So I look and I say, okay, end result goes in the top. Chances that the card is a heart. The heart is one of 4 suits. Okay? But here's what I have to watch even more for. You're sitting there going, ooh, this is going to be tricky. So, what are my chances of drawing the ace of hearts? Because given an ace is drawn, what's my chances that it's the ace of hearts? So my chances of getting the ace of hearts, given that it's an ace. Whatever I'm trying to find at the very end is what I'm reading into here. Here, denominator, yes. So the ace of hearts, there's only one of them in the deck. So there'd be 1 out of 52. Aces in the deck. Every card that you have in a deck of cards, there's one of them in each of my 4 suits. So there's an ace of hearts, an ace of spades, an ace of diamonds, and an ace of clubs. So the chances of getting an ace in the deck are 1 in 13, because there's 13 different cards in each of the suits. So if I set this up, 1 over 52, and remember, if you're dividing by a fraction, we multiply by its reciprocal. So we're going to multiply by 13 over 1. Multiply across, and then, of course, reduce. Now I'll wait till after number 2 to say it. We'll talk about the pattern then. But that's how I would work this. I'm trying to figure out what's the end thing that I'm trying to find, and then we'll divide by whatever that second part is, my given. So for instance, on this next one, the end result is the card's the 6 of clubs. Okay. So the odds of that we'll put up top. And no, you won't have to write it out in words every time, but I want you to be able to see it if you look back at the note packet. Given a club is drawn. Again, 6 of clubs, very specific card. It's not just saying a 6, it's not just saying a club, it's the 6 of clubs. There's only one of those in the whole deck of cards. Some of you are like, oh, there's 52 cards in a deck. Okay. A club is one of the 4 suits. So 1 out of 4. Okay. A specific card, just without a suit, is 1 out of 13. A specific suit's 1 out of 4. And then again, you just take the denominator, you flip it over, and reduce the fraction. Now here's where the pattern can come in and help you. Let's think about this for a second. Even if we go back to our spinner up at the top, we look at the final answer, we're like, the answer is 1 out of 3. Now could I have gotten that without doing all of this fancy stuff? If you tell me that the number was greater than 5 up here, there's 3 numbers, and that the number 7, well, the chances of getting any of those 3 numbers to be 1 out of 3, you're like, oh. And when I'm down here, if I'm told that it's an ace, I know there's 4 aces in the deck. Well, I'm looking for the one that's a heart. Well, what was my chances? 1 out of the 4 aces. Given that a club's drawn, there's 13 cards in a suit. What's my chance of getting any particular club? 1 out of 13. So if you use a little bit of logic with this, you can get to the answers without having to necessarily do all of the extra work that goes. But if it's not something that's familiar to you, maybe like cards, maybe it's better that we actually write them out. Now I'm going to keep writing them out, but I just kind of want you to think about it. So okay, The card is a spade. Okay. Card is a spade at the end. Given a black card is drawn. And again, the black cards are all the clubs and all the spades. So, anybody care to venture a guess on what the answer is going to be before we do it mathematically? A half, because half the black cards are spades and half the black cards are clubs. But we'll prove it here. So with a spade, again, I look and I go, okay, well, spades, there's 4 suits. So it'd be 1 out of 4. Then the probability of me getting a black card, half the cards are black, half the cards are red. So it's 1/2. And then again, I'm just going to take my denominator, multiply by its reciprocal, and our initial idea was correct. If I know it's a black card, I have a 50-50 or a 1/2 chance that it's going to be a spade. And again, if you can think of those stuff, snap, snap, cool. If not, not a big deal. That's what we got the formula for. Issues so far, except for those of you, of course, that have issues with cards, we can deal with that too. Like, no, it's the last day of the week, keep going. Okay. A 6-sided die is rolled. Find each probability. Okay. 4 is rolled. There's the magic word given. So a 4 is rolled. Okay, so I'm looking for a 4. Given that the roll is even. So when I roll a die, what's my chances of getting 4? 1 out of 6. What's my chances of getting an even number? 3 out of 6. Because if I think of the possible numbers I can get, those are the even ones. So 3 out of 6, or 1/2. And you're like, oh, okay. Because I look at it, I'm like, well, there's 3 even ones. I'm looking for 1, so it should be 1 out of 3. I agree it should be 1 out of 3. And it is 1 out of 3. That's the route we're looking for. But again, if you can just figure that out, drawing this out quick and going, wait a minute, there's 3 evens. Odds of getting this particular one's 1 out of 3. That's fine. We don't want to make more work out of this than we need to. Okay, let's see. Let's see if we can do some mental work here. A 2 is rolled. Given that the roll is less than 6, how many numbers are less than 6? 5. 1, 2, 3, 4, and 5. Okay, they're all less than 6. What's my chances of getting a 2 out of those 5 numbers? 1. Because there's only 1 2 that's available. But again, if I want to do it mathematically, I'd say, okay, a 2 being rolled is a 1 out of 6 chance. And then I'd be dividing by, the roll is less than a 6, which is 5 out of the 6 numbers. And if I work that out by multiplying by the reciprocal, the 6's will cancel, and there's the 1/5 we came up with. So that's the type of stuff that we're on the lookout for. Now, let's see if we can get ourselves into a little more of an issue here. All right. Given that the roll is a 3 or a 4, what's the probability of us getting an even number? Now, I think we can knock this one out. If you roll a 3 or a 4, how many even numbers are there? Out of 2 possibilities. Keep it simple. Keep it simple, keep it simple, keep it simple. Okay? All right. busting along here. So next we have what's called a contingency table. Now this looks kind of like what we just got done with on the last worksheet. So we have all these different possible situations. So these tables can be used to help us figure out our conditional probability. So we've got the lacrosse here. People that play it, people that don't, broken down by year with each one. So again, I want to know how many of each thing there are. So I'm going to go ahead and I'm going to total up each of my rows and columns just to be sure I've got all my information here. So let's see, 38 and 51. And I'm not doing the other one in my head. All right, let's see here. Let's clear out. Make sure our student population adds up here. So 2,095. So let's see here. That's interesting. I'm noticing when we were doing this before, their total up here, their total is off because notice they have 17 here and that's 14. They're wrong. So, how many students do we have total? I've never seen that on a worksheet from a actual company before. 2184. So there, they need to pay better attention to what they're doing. So I want to make sure on something myself here. 37 and 51. People got to keep an eye on me, I'm telling you. That's better. Okay. So I'm like, they're off 3, I'm off 4. So I've got my total numbers everywhere. And so I'm going to keep doing this just like I have before, except we're going to fix theirs because their total number isn't correct. So if I was trying to find the probability that a student plays lacrosse, given that they're a junior, I'd be like, okay, a student that plays lacrosse and is a junior. Okay, there's 34 of those. Okay, so I can't necessarily just read this. I got to take this into consideration too. So we're looking for a junior lacrosse player. Given that we already know they're a junior. So they did all sorts of things here. We're just going to give them the big old. So let's reduce this down. There will be a 1 out of 16 chance. Now, if I wanted to use it using all the fractions, because again, I shortcut it a little bit, I'm not going to lie. This would come from me doing 34 out of the total divided by 544 over 2183. If I was really following every step of the mathematics with this, that would be the way this would set up. 34 students that are juniors play lacrosse out of the total. There's 544 juniors out of the total. But the step I skipped in this particular case would be taking that and then flipping my second fraction, because the 2183s will cancel out and leave me with this total. So again, it's your choice. If you like doing the exact same thing every time and you want to keep using the formula, I say use it. But otherwise, I'd go back and just kind of simplify things a little bit. So a couple more here, then I want to throw one twist at you and we'll have you set. So again, here we've got ourselves a table. We'll do this first one. The table shows the attendance at a wedding. Find the probability that a person can attend the wedding given that the person is in the bride's family. Okay? So we have bride's family that's attending, because again, we've got to take it all into consideration, over that the person's just in the bride's family. I would just keep it as a fraction like this. Bride's family can attend. 104. Bride's family in total. 136. Yep. Keep it simple. Same thing with our baseball players. Okay? Find the probability of a student that plays baseball given they're a senior. So senior baseball player, make sure you take it all into consideration for your final result, over just a senior. Senior baseball player, 34. Seniors in total, 340. Reduce the fraction. Keep it simple. As we hit this last page, I'm going to do letter A on number 4, and then I want to give you one situation that you could run into on the homework that may be a little different from what we're seeing here. So, okay. Number 3. Just like we did before, we need to know how many people total are working here. So I'm going to give you all the numbers so we can keep life a little bit simpler for us here. Always good, just in case I'm asked for a specific part, how many of everything and everybody is. There's 2,200 total people working within our chart here. So again, keep it simple. Let's see here. Shopper uses a credit card given they're shopping at Jacob's Gas. All right. So Jacob's Gas credit customer over just a plain old Jacob's Gas customer. Credit card Jacob's, 456. Jacob's Gasoline total customers, 1140. Reduce that sucker down. That came out nice. That's how these all work. Keep it simple in pieces. No biggie, no biggie, no biggie. Now, I want to do one thing down here at the bottom, because there's going to be a type of question that gets thrown at you, and I don't want to throw you for a loop. If the word in the middle is then instead of given, that's going to happen. You are going to multiply instead of dividing. And I'm just gonna give you one example of what you could get down here with that, and then I will be done. Draw a heart, bless you, from a deck, then a diamond. Okay, notice it doesn't say given it's a diamond, because that would be kind of hard to get a diamond that's a heart. That'd be kind of strange. So what I would do is I'd say, okay, draw a heart from the deck. Well, the heart would be 1 out of 4. Okay. But then I got to be careful, because remember, this 1 out of 4 is coming that it's 13 out of 52, because there's 13 of each suit. Then a diamond, be careful. If I took a heart out of the deck, how many cards are left? 51. But there'd still be all the diamonds because I took a heart out. You're going to have to think a little bit. And then instead of dividing, I just multiply them. And again, the assignment that we wrote up at the front is what you've got. You've got a little blend of these, and there's going to be a packet coming your way on Tuesday. But I'll have answers and keys ready to go for you then.